All right, so we left off with multiplication arrays. So decimal. There. So we'll start off slow. It's Monday. We'll warm up a little bit. So first, what I'd like you to do is illustrate and use the illustration to come up with an answer. How about 8/10 times 6/10? So draw a quick sketch of that shows what the answer ought to be. We'll try a little more complicated one. There's a bunch of different ways to draw it. I shaded in two directions and just grab the overlap. Sometimes we just shade each part. That's one way your picture could look. Questions on the basic one? Probably more excited. How about 1 3/10 times 1 4/10? This one we get a piece of graph paper for. Downloaded one the other day. There. this one? Not bad? So on this one here, I got the expanded version up here, which is based on my picture. So reading it over this way, here is my 1/2, and here's my 3/10, based on this being the whole. And this way, I have my 4/10 and my 12/100. And I should make a note that I can trade some of those hundreds in for a 1/10. And then since most of us are going to be teaching the standard algorithm, we should show that too. And that's what we did on the worksheet the other day. Questions on that? Cool. All right. So what's our algorithm then for multiplication? So this is a model. How do I do it without drawing a picture? Jumping straight to the algorithm. What's the key?
It's 3/10 times 2/10. You times the numerators and the denominators.
If you write them as fractions, okay, what about not using fractions?
When you stack them on top of each other, you times them like a normal You basically make the decimal places, you ignore them, and then your answer has to have the same amount of decimal places as the two added.
So we multiply ignoring the decimal place at first. So this is just like multiplying 13 times 14. And then you'll notice I highlighted as I was moving through here that there were 2 fractional decimal places in the problem. So there's 2 fractional decimal places in the answer, and that's only where to put the decimal place after I multiply it. So that's the algorithm, right? That's the process, the rules that get it done. Does it have anything to do with base 10 blocks? Nope, it's just how to do it for other numbers. These pictures get harder to draw if you try to show anything other than like 1s and 10ths. It becomes impossible to draw. So when we're trying to illustrate it with kids, we keep it super simple with problems like this one and problems like this one. And we're not really trying to test them on explaining it, but we want them to try it. And we're just testing on how in schools at that point. You guys, on the other hand, you get to explain. So that's multiplication. Let's take a look at division now. So I'm going to put up a division problem, and I would like you to, I have the base 10 toys up here if you want to grab those. I want you to think about why you get a certain answer when you do this division. So let's start off with, oops, pen, maybe. Highlighter. One and 2/10 divided by 3. So I know you know how to do that using whatever method you like. So do it out how you normally would, but then think about how you might try to explain why the answer is what it is. And you can use base 10 blocks if you want, or any other kind of way to justify it. Think about the models we had for division. Anybody remember the models we talked about with fractions? Areas multiplication. What were our division lines? We have 4 of them. How about groups in? Remember that one? How many groups of this are in that? Another one was called the set partition. I need to split up all this stuff among my 3 friends. Okay, slightly different perspective on it. What's another one? Repeated subtraction. Nice. And there were 2 names for the other one.
Missing factor.
Missing factor, or what do I multiply by? Yeah. So those are the models that we used for whole numbers. They kind of work okay with fractions for the most part. Could any of these apply to the problem that we have at hand here? That's why I'm going to play with that for a little bit, think about it, knowing what the answer is. And then I'll go over a couple of perspectives I have on it. All right, so I wrote a bunch of ways to think about it, and maybe you went into one of these, maybe you played around and nothing came out of it, and that's okay. So the first model we talked about is groups in. That would lead you to ask, how many groups of 3 are in 1.2? Well, there's not a whole group of 3 in 1.2, right? So then we have to go back to thinking about it the way we did with fractions and those crazy pattern blocks, and that kind of hurt our heads a bit. We could do it that way, but it's going to be a little tricky. So this one is questionable. split 1 2/10 into 3 groups, how many are in each group? That makes me think of money. If I had $1.20 and I needed to share that among 3 people, I could totally make change and do that, right? So this one seems pretty doable. So I got a lot of faith in this one right here. Repeated subtraction. How many times can you subtract 3 from 1.2? That kind of brings me back to this one right here. I can't do it a whole time. So that's going to require you to really think hard. Little question mark right there. And then what do I multiply by in the missing factor model? Would lead me to say, what do I multiply by 3 to get 1.2? Oh, well, 1.2 is a fraction of 3. So I just have to figure out what is the right fraction here. Okay, so that's kind of like the first and the third one, I think. They seem pretty similar to me. I'm going to go for that second option, the looking for splitting it into 3 groups. And so to do that, I'm going to grab my online toys here. They have a zoom in, don't they? Or am I zoomed in as far as I can, probably? All right. So if we've been using this as a whole, so this would be 1 2/10, right? So in order to split this into 3 groups, wouldn't you agree I just need to trade a whole for a bunch of tenths? So I think they have a shatter button here, don't they? Yeah. This one? Yeah, break into pieces. Okay, so click there, break, bang, there it is. So now I can start grouping in 3. So there's a group of 3, and then I can find another group of 3, and another group of 3. So I think this is answerable. Oh, and there's another group of 3 right there. So it looks like there are 4. Oh, wait a minute. What do I have here? Oh, I did that wrong, didn't I? I wanted how many groups?
I wanted 3 groups.
I wanted 3 groups. I did the wrong question. Okay. So let's share and share. Okay, now I have 3 groups. How many is in each group?
4/10.
4/10 would be the answer. Yeah. So let me restate that. Thank you for straightening me out there.
Where did the other 4/10 go in the picture?
What's that?
Where did the other 4/10 go in the picture? One of them is missing a 4/10.
Oh, nope, we're still good. Let's see, new page, screenshot that thing. Oops, kind of spread out, but that's okay.
See what one is.
Oh, one's hiding somewhere.
Is it behind the 3?
Behind somewhere? They were all there a minute ago, weren't they? Oops. Let's see, can I highlight a group? Where is it? Oh, it was underneath. Thank you.
Yeah.
You were right. You're right on the ball today. Get a close eye on me. All right, let's clean them up a little bit. Oops, come on. Ooh, okay, this is behaving strangely. I'm just going to steal it while I can. Ooh, I have 2 pictures now. There we go. All right, so we'll state the question and the answer again. So the question related to the problem, 1.2, 1 2/10 divided by 3/10, is to split 1 2/10 into 3 groups. It's called the set partition model. How many are in each group? And so then we can say there are 4/10 in each of the 3 groups. So we can model it out. Not too bad.
Did you use that same thing for how many groups of 3 are in 1 2/10? Use that same one.
How many groups of 3 out of 1 2/10? So let's try it. So I'm going to redraw it a little bit different. after that. So 1.2 divided by 3. 3 goes into 1 2/10. So,
I thought that's the one we just did.
no, we did the set partition. We want to split 1.2 into
Okay.
3 groups, right? Slight different twist there. So how many groups of 3? 1 2/10. So here we can definitely change our perspective. So instead of thinking of that as 3 wholes, we can just think of that as 3 things and be a little more general. So then we have our 1 2/10, which I'll grab another picture of. Let's see, I trash everything here. No, I hit the trash button. There we go. 1 2/10. Let's screenshot that. And again, this is easier with physical toys, so feel free to grab some physical toys at any time. And so I can just start looking for groups of 3. So this has a nice grid on it, so I can kind of feel that out. So here's one group of 3. Here is another group of 3. And here is another group of 3. Problem though. What does it look like we should state for the answer?
4, but then I did the same one. But then since there's a decimal point in the thing, I figured, you could just say like in multiplication, you have to have the same sort of decimal points.
Yeah, that is true. When we switch from multiplication, oh, is that true? Yeah, I think that should be true. We should have the same number of decimal points. Oh. That's not always true.
Yeah, that's what I was afraid of.
Darn.
I know it works here, I wasn't sure.
Yeah, it's not always true that you're going to have, it only is true. Ooh, I don't even know that. Okay, I was going to say it's only true if there's no remainder, but I'm not even sure if that's true. So.
This to me seems really hard because it's not an obvious. You have to, for like kids, you already have to have knowledge.
Right, yeah, so we're trying to brainstorm our knowledge to justify this. And although we can get a 4 out of it, the 4/10 is kind of fuzzy, justifying that it's 4/10. All right, I'll make a note to rethink that. All right, so that didn't look like it worked so well. So I'm just going to go back to the way we did fractions before. Poised to do that. I think this is going to hurt our brains sufficiently. So here, and I'm going to have to zoom out, I think, to show all this. All right, that should be more than far enough. And there's nothing significant about that highlight there. So this is back to that 3 goes into 1.2. So we have this group of 3 trying to go into that little group of 1 2/10. And we can see it doesn't go in a whole number of times. So then the question is, what fraction do we have here? Well, what's kind of a common denominator we can use to talk about this? Literally, common denominator. Tenths, yeah. So if we describe each of these as tenths, it might be doable. So how many tenths do we have here?
30 tenths.
Yeah, so this would be 30 tenths. And what do we have over here?
12 tenths.
12 tenths. So of the 30 that we're looking for, right, isn't this what we're looking for? How many do we have? We have 12 of them. So the answer should be whatever 12 over 30 is. See if that works out. Does 12 over 30 reduce?
Yeah, 4 tenths.
4 goes in there, or let's see, 3 goes in there, and we get 4 tenths, which is what we believe the answer to be. So using that same fraction technique we used before with the pattern blocks, we can work it out. But just like those pattern blocks with division hurt our heads a significant amount, this is pretty tough to think about. So this isn't something I would present to kids.
With
It's good for
that,
us. Yeah.
the only thing I get it, but would it be hard where that's not a complete reduction? in a
Yeah,
fraction?
and that's going to happen sometimes. So we're working up to that. Yeah. So let's try another one. So here we were just dividing by a whole number, right? So let's take one where we do something like 2 divided by 0.5. So you all have learned how to deal with division with decimals. So come up with an answer and then think about our models and see how you could justify that answer. Okay, so we all know an algorithm for this. Do whatever algorithm you like. Come up with an answer. And then think about our 4 models, and if you can use one of these and or the toys to make sense of it. Give you another minute, and then I wrote out 4 questions based on our 4 models to see which ones would be useful. So the first model groups in, I could ask how many groups of 5/10ths are in 2. And I think I can make sense of that one. That's not too bad. So here's a group of 5/10ths right there. There's another group of 5/10ths right there. There's another group of 5/10ths right there, and another group of 5/10ths right there. So it looks like there are 4 groups of 5/10ths in there. Now, I can even go further because I can use long division like we learned with whole numbers. The trick of long division was to make a guess on the multiple, do the multiplication. What's 4 times 5/10ths? 2, and then subtract. And hey, that works out great. The blue question is about that set partition model. Split 2 into 5/10ths groups. That sounds a little strange. How many are in each group? I could switch it a little bit because 5/10ths is a nice number. What's another way to refer to 5/10ths? Bless you.
Excuse me, 1/2.
1/2, yeah. So I could say split 2 into half a group. Oh, if 2 is a half a group, what would a whole group be? 4. Oh, that kind of worked out. Now, if that was 3/10ths, that would be a little trickier. Okay, so then we get ourselves a little bind. So last time, the splitting into groups seemed to work well, but this how many groups of didn't work so well. This time, how many groups of are in, that's working well, but the splitting into groups isn't working so well. You see we got a little problem with division and decimals. It's tough stuff. But we're going to resolve it into an algorithm pretty quick. So let's see. Next models we had to choose from. How many times can you subtract 0.5 from, or 5/10ths from 2? That's not too bad. We've already learned decimal subtraction. So we can take 2.0 and subtract 0.5. Remember with decimals, we have to line up the decimal point as our algorithm for subtraction. And I can borrow here. And that works out quite lovely. And then I can just keep repeating that until I run out of 0.5s to subtract. And I can see it took me 4 subtractions before I got rid of 2. And then if we've done a whole bunch of practice with multiplication, this last method, what do I multiply by? That might not be too bad either. So let's think about that. I have to multiply something by 5/10ths to get 2. And there's a couple of perspectives you could take on it. Anyone want to try to explain an answer in this context? How could you justify an answer there? What do I multiply by 5/10ths to get 2?
Look at 5/10ths as half of a whole.
Yeah, that works. And you could say 4 has to be what to multiply by. Yeah. So you can see that as a half. Another way to think about it is I need to multiply 5 by something to get something related to 2. I know 4 times 5 is 20, but I've got a decimal point in there. So there's a couple of different ways we can guess at 4 as the missing factor. But it's a kind of guess and check kind of thing. And even with whole numbers, that's the way it is. You know, think about way back when we were doing whole numbers. 12 divided by 3. What do I multiply by 3 to get 12? If the kids are good at their multiplication facts, they're going to get it instantly. If they're not, they're going to guess and check. 3 times 3, nope, that didn't work. 3 times 4, maybe they count on their fingers. Oh, that's the one. All right, so let's do a couple more examples and then we'll nail our algorithm down. New page. How about 2 4/10ths divided by 4/10ths? So think about that in terms of an answer and a model. So I thought about it in terms of the groups in model, how many groups of 4/10 are in 2 and 4/10. And we can see there's 6 groups in there, it goes in 4 times. So sometimes one model works better than another. It depends on the division problem. One more, and then we'll go over the algorithm. How about 8/10 divided by 5/10? So that model we use for fractions mostly works when we play with decimals. I'm looking for a group of 5 things, right? So I have 5/10 here. I have 8/10 over here. And sure, I have 1, but then what do I do with the fraction under that little remainder? How do I do with that?
Wouldn't it be 3/5?
Yeah, I have 3 pieces out of 5 that I'm looking for. So one way to state the answer is 1 3/5.
Wouldn't you need to stay in decimal point, so it would be 1 6/5?
Yeah, and we could definitely rewrite that into decimals and call it 6/10 after. So here's one thing that was kind of a common theme to all the problems we did. Anytime we tried to think of looking for groups, we ended up looking for whole numbers of things. Whether it was 3 things in that first problem where it kind of failed on us because we missed out on the tenths part, but every time we were looking for a whole number of things. And there's 2 reasons for that. And the main one is just the way we learned long division. The long division algorithm that we're very familiar with, and the kids will be kind of familiar with, they'll still struggle with it, is it's looking for groups, is the whole premise. And when we're looking for groups, we're counting. And we tend to count with whole numbers. Okay? And it turns out, because of the way division works, whenever I do a problem, like 1 2/10 divided by 3/10, for example, that can always be written as a fraction. And any fraction can be rewritten so that we have a whole number denominator. Or the problem is just in whole numbers. And usually we just focus on the denominator. So another problem we dealt with was, let's switch color, 2 4/10 divided by 4/10. When we draw the picture in terms of tenths, we're essentially multiplying top and bottom by 10 to get whole objects to play with. And the problem we ended up looking at was we had 24 things and we were looking for groups of 4 in there. Isn't that ultimately what we ended up doing? And that's the key right there. That as long as we start looking for whole numbers of things for accounting, any division is going to work out right. There's one other trick to it. So the division algorithm for decimals. There's 2 parts. One is we want to adjust the numerator and the denominator. So the denominator is a whole number. And then 2, we use the numerator to figure out where the decimal goes. So in fraction form, they're called numerator and denominator. What's the denominator called when it's in division mode, not fraction mode? So for example, back here, here's numerator and denominator. What are they called when I write them like that? The whole thing is the quotient.
Dividend and divisor.
Dividend and divisor, yeah. So here I'm referring to numerator and denominator. Over here, there's dividend and divisor. All right, so we have all this language we use, and the kids are going to be using all these words too. And so we want to make sure every once in a while we stop and we make them. The numerator is our dividend, and the denominator is our divisor there. And that evens out all the problems. We're always dividing by a whole number. So now we take a different problem. Like that 5/10 goes into 8/10. We focus on the denominator first, and we want to adjust its decimal point. Have to equally adjust this one. Essentially, we're multiplying top and bottom by 10. We do that for 2 reasons. One, it's way easier to think about whole groups than fractional groups when we're doing division. Right? Just think about some of those pictures we drew earlier. How many of those hurt our brain? A little bit. That's a bad thing. And the other thing is now we know where the decimal has to go in the answer. It's usually a good idea to try and get kids to rewrite it. So what do I call the divisor now? 5 instead of 5/10. And what do I call the dividend? 8, and I know the decimal now goes to the right of the 8. Now thinking about whole numbers, does 5 go into, how many times does 5 go into 8? Once. 1 times 5 is 5, subtract -3, and then we fill in zeros. And since we know where the decimal goes, we don't have to worry about that fractional part anymore. Now I can just think about it as if it's 5 going into 30. How many times is that? 6 times 5 is 30, and we're done. So we get the 1 6/10. So there are some simple decimal problems we can play with in terms of looking for groups, but they have to be picked really carefully. So for example, this one is a bit tricky. Even though 12 and 3 seem to go together right, it's just the way we try to put them together. This one worked really nice. That was about the easiest one we did. How many groups of 4/10 are in 2 and 4/10? So if we carefully pick those problems, we can then lead students into saying, hey, look, we're just working with whole numbers. We just got to adjust the decimal points to make it happen. So that's the algorithm for division. Okay, next, we've got a couple more things to tie up. Let's see, in 7-2. So we talked about rounding before, and rounding is just a matter of identifying the right place value. And that was kind of going on in section 7.1. We're going to take that just in a slightly different direction with the idea of significant figures. So, did I bring it up? Yes, I did. All right. So let's switch the video for a second. Online. How do I do that? Right there. All right. So I have a wooden block. See my wooden block? Everybody see my wooden block? So I grabbed this out of my room of toys earlier, and I have a scale in the other room, and I dropped it on my scale. And my scale told me that this was 30 grams of mass. And then anybody want to guess how many centimeters wide that is?
3.5.
3.5. Okay. What do you think?
I was thinking
5. Okay. 3.5 and 5.
4.
4. We're going 4.
I'll go with her 4.
You're going to go with her 4. Okay. So it's pretty well cut, this block is. I paid a lot of money for it, so it better be. And it's pretty darn close to 4 centimeters in each direction. Right. Switch back here. All right. See, y'all saw my block. All right. So significant figures. What the heck does that have to do with my
Can we take a
silly
quick
block?
potty
What's that?
break? I'm sorry, I have to pee so bad.
Okay. We're going to take a potty break. I'm going to stop this video and come back with another.